Okay, so in the past few classes, we've seen different compression algorithms. We first looked at optimal compression algorithms for IID sources. We started with the Shannon code, and then we saw the Shannon-Fano code and Huffman code, and then we saw that if you want to do blockwise encoding, then these codes are not really efficient in the sense that the Huffman code would still achieve a rate close to entropy, but then blockwise encoding is computationally very intensive. So I introduced arithmetic coding as an approach to have reduced encoding and decoding complexity, but the rate is still close to the entropy. But all the algorithms that we discussed till then only worked for IID sources, in the sense that they were optimal only for IID sources. You could still use them for non-IID sources like Markov chains, but the rate that they could get to was only equal to the first order entropy of the source. On the other hand, if we have a non-IID stationary and ergodic source, then the minimum rate of compression is equal to the entropy rate. And that, as we've seen using the example of a Markov chain, this can be much smaller than the first order entropy h of x. Right? So for a long time, people used approaches similar to Huffman codes or Shannon codes or Shannon-Fano codes in order to design compressors even for sources with memory. But then in 1977 and 1978, Abraham and Lempel and Jacob Ziv introduced a class of algorithms, which are now called the Lempel-Ziv algorithms after them. And these are universal compression algorithms for stationary and ergodic sources. So firstly, they achieve an asymptotic rate equal to the entropy rate of the stationary and ergodic source. But at the same time, it is also universal in the sense that it does not require the true probability distribution as the input. So irrespective of what the sequence is, irrespective of what the true distribution is, as long as you have a large enough file, as long as n tends to infinity, the asymptotic rate always tends to the entropy rate. But of course, there's a slight trade-off over here. It's good asymptotically, but for small block sizes, for small n, this is not optimal. So really, if n is very small, then you should not be using something like the Lempel-Ziv algorithms. You should be using something like Huffman codes or the Shannon-Fano LIS or arithmetic codes. So the general approach towards that is followed in the algorithms proposed by Lempel and Ziv is the following. You take your input sequence, you take the source sequence xn and partition it into phrases. So a phrase is basically a subsequence of the string that we have. So you partition them into contiguous substrings or phrases and then encode each phrase separately. And the basic idea is that you use the previous phrases to encode the current phrase. You use the previous phrases as dictionaries. So hopefully there's a lot of information contained in the previous phrases, so you can get a very compact encoding of the current phrase, given that you already have the previous phrases. And both the encoding and decoding starts from x1 and goes all the way to xn. So there's an order in which you encode and decode the symbols of the string. Okay, and in the previous class, I had just introduced the LZ77 algorithm, and it works as follows. So the way you construct the phrases is the following. The first phrase is always equal to the first symbol, x1, and then we move in a recursive fashion. So suppose we have parsed x1 through xi into phrases. So the next phrase starts with xi plus 1. Now if xi plus 1 has not seen before, so if xi plus 1 does not occur in the substring x1 through xi, then xi plus 1 itself is the next phrase. If If it has occurred previously, then you look for the longest match. So you go from x1, xi plus 1, xi plus 2, xi plus 3, all the way up to xi plus l. So you find the largest L such that the string of length L starting from xi plus 1 matches with another subsequence in x1 through xi. Okay, and that gives you the next phrase. So the longest matching subsequence observed previously, that gives you the next phrase. Okay, and how do we encode this? I haven't really told you how to encode it in binary, but at a high level, the encoding works as follows. You store two things, two or three objects. So if there is no match, which happens in the first case, then you store a bit 0, indicating that there is no match, and then the symbol xi plus 1. So this information is enough to reconstruct the current phrase. If there is a match, then the first bit is 0, indicating a match. And then you need two things in order to recover the phrase: the location of the match and the length of the match. Right? And this much information is enough in order to decode the symbol. Okay. So to take an example, if we have a so if this is the string, then the first phrase would be A, the second phrase would be A, the third phrase would be AA, the fourth phrase would be B, and then C, and then ABC. And how did I get this? So note that the first symbol is always the first phrase. For the second phrase, you start with A, only A has been seen before, so this becomes the next phrase. Now, at this point, have we seen A before? Yes, we have seen A before. Have we seen AA before? Yes, this occurs as a substring previously. So that is going to be the next phrase. And then now we are at this point. Have we seen before? No, we haven't. So that becomes the next phrase. Right? Have we seen C before? We have not. So that becomes the next phrase. And have we seen A before? We have seen A before. Have we seen AB before? Yes, we have AB. Have we seen ABC before? Yes, we have seen ABC. Right? So ABC is the next phrase. Now, can one of you tell me the encoding for this particular sequence? Yes. So what will be the encoding of the first phrase? What's the encoding of the first phrase? So why 0, 1? It's A, right? It is 0, A. Right? It is 0 followed by X. Right? So it's a character, and it's a location and the character. Right? So now what about the second phrase? right? So it's 1 because there is a match. The location of the match is basically x1, so x1 is matching. So it's 1 and the length of the match is 1. Okay, what about the third phrase? It is 1, location of the match is 1, length of the match is 2. Third phrase, sorry, the fourth phrase, it is 0b. The next, it is 0c. And what about the last phrase? It is 1 because there is a match. The location is the fourth location, so it's the fourth symbol. And the length of the match is 3. Right? So this is this is the encoding of each phrase. So the encoding consists of a bit and then either a symbol xi plus 1, or it's going to contain two integers, two positive integers, which corresponds to a location and a length. Okay, so any questions? Any questions regarding the algorithm or anything previously discussed? Okay, so let us perhaps think about it. So how many bits, if we used sort of fixed length encoding for each phrase, then how many bits would we require to encode each phrase? Now let us look at the first case. All right, case 1, where it is bit 0 followed by a character. So how many bits are required in this case? So basically you would store 0 followed by the encoding of the character in binary. So how many bits would this require? Well, it depends on the size of the character, right? So it would be 1 plus log cardinality of x. If it's an ASCII character, then yes, it would be 1 plus 8, which is 9 bits. But in general, this would be 1 plus log cardinality of x. Okay, so this is fine. It doesn't seem to be too much. What about case 2? Right, so it consists of bit 1 followed by a location and then the length. So if we used a fixed number of bits to represent the location and a fixed number of bits to represent the length, then roughly how many bits would we require? Right, so roughly 1 plus, so the maximum value of that the location can take is, so the location can be anywhere between 1 and n minus 1, right? And so the location can be as large as log of n minus 1, n minus 1. So it's roughly 1 plus order log n, let's say log n itself, log n, plus the length of the match could also be large. So it could be as large as log n, or some constant times n, right? So in the worst case, this would be roughly 1 plus 2 log n. Right? So this is the number of bits that would be required in order to store a particular phrase.
Sir, are we store encoding locational length using fixed length also?
Correct. So this is if we used fixed length encoding, then this would be the case. So, all right, so this is a big qualifier. So if we use fixed length encoding for each phrase, then we would require 1 plus 2 log n bits, right? And but what is the maximum, or what is the order? What is the maximum order of the number of phrases that we can have? Right, could be order n, right? So maybe it's possible that the number of phrases is n, right, or some constant times n. So if the number of phrases is order n, then the total number of bits to represent right, it would be order n log n. So it means that we don't really get any compression. We're only blowing the size of the sequence up, and clearly that's not optimal. So the only way we can get compression is by using variable length encoding to store both the location and the length. Okay, and we'll see in a bit how we can use variable length encoding to reduce the size of each, to reduce the number of bits required to store each phrase. Okay, so clearly fixed length encoding is not good. So but before I discuss how we are going to do variable length encoding for these locations and lengths, let me also introduce the other algorithm, the LZ78 algorithm. Okay, but one more thing I'd like to point out is that although I've given one particular description of the LZ77 algorithm, there are small variants of the algorithm, and they're all basically still called LZ77. So minor changes depending on the implementation are could be the following. So first, this again depends on where you take the match. So for instance, so let's say that we are at this particular location. Let's look at the third phrase. When I'm looking for the longest matching phrase, I'm always considering a match. So the entire substring over here, starting from this point, should match till this point, right? And I'm basically not allowing an overlap. So in principle, another way of an alternative parsing into phrases could be the following. So let's say that I'm trying to parse the second phrase. So let me write it separately. Okay. So I have A, B, C, let's say. Okay. So the first phrase is going to be A. The second phrase, so if I look at this matches with only this from what I've seen previously, right? But then if I look at AA, this matches with this AA, right? So if I only impose that the location of the match should be less than I, less than or equal to I, then I could potentially get a smaller number of phrases. So for example, one encoding, so I could say that my first phrase is A, my second phrase is AAA, my third phrase is B, and my fourth phrase is C. Okay, so this is different from the rule that I discussed previously. So this would be encoded as 0A. The second one would be encoded as 1, 1, 3. The third phrase would be 0B, and the fourth would be 0C. Okay, so let us see how we would decode this particular sequence. So you first observe 0, comma A, so it's a new character, and you know that the first phrase is A. Now let's look at the second phrase. So this is 113, which implies that there is a match. The location of the match is 1. So the first character is A. The second character of the second phrase is the first character of the second phrase, which we know is A because we just got it from this. And the second character is A. The third character is also A because this is a match. Right? And the third phrase is 0B, which means that this is decoded as B. The fourth phrase is encoded as 0C, which implies that the phrase is just the symbol C. Okay, so this is a minor variant of what I have discussed. Asymptotically, all of these are optimal. It doesn't really make much of a difference, but when you implement it, there are a lot of optimizations that one can do. Another optimization that people typically do is instead. So here, when you're looking for a match, you look for a match all the way from the first location up to the third location, up to the ith location, right? But instead of that, you can search for a match not from 1 to I, but instead from I minus W to I for some fixed W, where W is typically called the window size. So it's as though you're taking the entire sequence, you're moving a window as you keep going on and on. You're taking this window and you're moving it from left to right and are searching for a match only within this window. And that is why it is sometimes called sliding window limpensim. Okay, so I see a question regarding the previous one. So let me take this example once again. Or let's take another example. Okay, so let us say that the sequence that I want to parse is this: ABC, 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 ABC. Okay, so to parse this, I use the following modified rule. Okay, so the second rule is now modified. So find the longest match that is xi plus 1 up to xi plus L should be equal to x j plus 1 up to x j plus L for any j between 1 and I. Okay. So note that this statement, so I'm looking for a match from, so the starting location of the match can be anywhere between 1 and I. On the other hand, when I previously discussed this, the starting point of the match should be between 1 and I minus L. Right? So basically, I'm allowing an overlap between the match. Shouldn't J be strictly less than, sorry, so it's less than or equal to I minus 1. So it's greater than or equal to 0. So J should be between 0 and I minus 1. Thanks for pointing that out. Okay. So now if I have this modified rule, then can you tell me what the parsing would be? So I have ABC, 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 ABC. Okay. Now what would the first phrase be? Sure. So it's just A. Right. It would be encoded as 0, comma A. What would the second phrase be? Just B. Right. So you would encode this as 0, comma B. What would the third phrase be? C. So this would be encoded as 0, comma C. Now what would the fourth phrase be? Exactly. So the fourth phrase would be this entire string over here. ABC, ABC, ABC. And what would the encoding of this be? Right, so it will be 1, 1, 9. So let's see how we would try to decode this particular. So this is the encoding. So if you want to recover this particular string, then you look at 0, comma A. You know that there is no match, so this is decoded as just the symbol A. This is decoded as the symbol B. This is decoded as the symbol C. Now we have to decode this. So you start from location 1. So this comes here. So it's A. So the location is 1 and the length of the match is 9. So 2 and 3, 4, 5, 6, 7, 8, and 9. Right? So this is how we would decode the string, given that this is the encoding. You start with that particular location, and then you go along. All right. Any questions? Sure. So this would be slightly preferable over the previous one because this gives you fewer number of phrases, right? So the size of each phrase would be larger. Right. So again, there are many different minor modifications that you can make including this and including having a sliding window. So you search only up to location I minus W instead of starting from location 1. And there are other changes as well. So the way you define the phrases. So some people take this to be the shortest. So this is the longest phrase which matches with anything that has been seen previously. Sometimes they take the longest phrase plus the next character that is encoded as the next phrase. And yeah, there are several such things that one can do. But ultimately, all of these are asymptotically optimal. So disadvantages of this method. So once again, if the length of the sequence is very small, then this is not very good because you will need a large number of bits to encode each of these phrases. But we'll see as n is very, very large, the number of bits that would be required to encode each phrase would not be too much. So for n being very large, the number of phrases would be small, and therefore you can the overall compression length would still be pretty small. And of course, there are other optimizations that you can do. As I mentioned, if you take a finite window length, then depending on the size of the window, the size of the phrases that you would get would change. So the larger the window size, the smaller the compression length. But the larger the window size, the more you have to search over the string. Right? So to get the next phrase, you have to search from I minus W to I. So the larger W is, the more you have to search, and that would increase the encoding and decoding complexity. Any other questions? All right. So yeah. So ultimately, what you're going to store is going to be either bit 0 and a character, or bit 1 location. Let's call it for the ith phrase. This is going to be whatever location Li and the length of the match Mi. Right, and it turns out that you can obtain a variable length encoding of these, which instead of requiring 1 plus 2 log n bits, you can store it with just 1 plus order, sorry, 1 plus log Li plus 2 log log Li plus log Mi plus 2 log Mi bits. So it turns out that this number of bits, or roughly this number of bits, actually suffices to encode this particular phrase. And we'll see how to do that in a couple of minutes. Okay. So now let's see the other Lempel-Ziv algorithm, which is called LZ78. So this is called this is also sometimes called tree-structured Lempel-Ziv, because this has the interpretation of constructing a tree. Okay, so I'll come to the tree interpretation later on, but the way you parse the sequence into phrases is the following. So the first phrase is still the first symbol xi. Now suppose that we have already parsed x1 through xi into phrases. The next phrase is going to be the shortest phrase which has not been seen before. So it's the shortest subsequence xi plus 1 through xi plus l, which is not already a phrase. Okay. So it's basically it's going to be a subsequence which can be written as the longest matching phrase plus a new character. Okay. And the way you encode this is basically you just store the location of the matching phrase and then a character. So let's see an example to understand this. Take the previous example, A, B, C, ABC. Okay. So now recall what the algorithm tells you. So the first phrase is x1. So it is this. So what is the second phrase? So it is the shortest subsequence, which is not a previously seen phrase. Or it is the longest matching phrase followed by the next character. So any guesses? What is the next phrase? It's AA, right? Because AA is the shortest phrase that we have not seen before. So what is the next phrase? AB. Good. What is the next phrase? C. Right. What is the next phrase? ABC. Good. Okay. And what would be the encoding? How would you encode the first phrase? So if there is no matching phrase, then you can just store the location to be, you can take the location to be just 0, right? So this is the first phrase, this is the second phrase, and so on. So the 0th phrase would be no match. So the first would be encoded as 0A. What about the second one? So how would you encode the second phrase? So note that the encoding of every phrase is a location followed by a character. Right, so it's just 1 comma A. What about the next phrase? What is the encoding? It's 1B. The next phrase, it is 0C. The next one, so it's actually the index of the previous phrase. So for example here, AB matches with this phrase over here, and this is the third phrase. So this would be third, the index of the matching phrase followed by the next character, which is C. Okay. So let's see another example. Consider the following sequence, all A's.
Sure, what would we have done if there was no C at the end?
If there were no C at the end,
Yeah.
then okay, yeah. So then you would store it as the matching phrase followed by just an empty character.
Empty character as in like.
So you just, in your alphabet, you just include an empty character, which is basically encodes no character.
Okay, yeah, yes. Correct.
And yeah, so the last phrase is a little bit tricky, and yeah, one way to solve that is, yeah, you can append an empty character to your alphabet and use that to encode. Okay, so let's see another example, which is basically all A's. Okay, so what would be the LZ78 parsing? What is the first phrase? So it would just be A. What would be the second phrase? AA. What would be the third phrase? Yes. So the third phrase would be 3 A's, not 4 A's, because it always has to be the form a phrase followed by a character, not a substring followed by a character. So it would just be 3 A's. What would be the fourth phrase? Right, so it would be 4 A's, not 6 A's. Right, so the LZ78 parsing is always some phrase followed by, so it is the longest matching phrase followed by another character, not the longest matching substring followed by another character. Okay, and so on. So the encoding would be 0A, 1A, 2A, 3A, and so on. Right? It's always the previous, for this particular example, it is the previous phrase followed by A. Correct? So this would be the LZ78 parsing. So how do we decode this? So you look at 0A, this is decoded as A. The next phrase is obtained by appending an A to the previous phrase. So you take the previous phrase and then append an A. Now this is obtained by appending an A to the first phrase, to the second phrase. So this is AA followed by an A. This phrase is obtained by appending an A to the third phrase. So this is AAA followed by A, and so on. Okay, so this would be the LZ78 parsing. So what can you say about the length of the ith phrase? Right. So it's equal to I. Correct. Now compare this with the LZ77 parsing. So in the LZ77 parsing, you don't restrict each phrase to be, you don't restrict the next phrase to match with some previous phrase. As long as it matches somewhere in the sequence, it's good enough. So what would be the LZ77 parsing of this sequence? What is the first phrase? It is A. What is the second phrase? Right. So if you go by the first description that I had, then it is just A. What is the next phrase? It is AA. What is the next phrase? It is 4A's, because you're at this point and you have a match of size 4. So it is 4A's. And what is the length of the next phrase? 8A's, right? And so on. Right? So the parsing obtained using LZ78 and LZ77 are going to be quite different. All right. Any questions? So one natural question is, well, if you already have one optimal algorithm, then why do you need another? Right? And it turns out that there are certain trade-offs. So in general, the LZ77 algorithm, if you choose a large enough window length, then you get a better compression rate than you can get with LZ78. Because the number of phrases that you obtain using LZ77 is generally lower, or in practice, it is lower than that of LZ78. But the LZ78 algorithm is actually much more efficient than the LZ77 algorithm, because there is in fact a tree. You can construct a data structure like a tree, which lets you very efficiently encode and decode. Whereas for LZ77, you have to search through an arbitrary window of size W for a match. Whereas in LZ78, you're not looking through the entire string, you're only looking for phrases. So the search space is in fact much smaller. All right. But of course, I mean, there are different variants. So the ones that are used in practice are slightly different from what I'm describing over here. Okay. So now the only question that perhaps needs to be addressed is, how do you actually store these in binary? So ultimately, all of these would require you to store some bits, some characters, and then certain positive integers. And storing the bits and the characters is fine, but storing the integers takes a lot of space, and we want a more efficient way to do it. Right? So ideally, what we want is a prefix-free encoding of the positive integers. So if we can come up with a prefix-free screen for any arbitrary integer, then we're good. So suppose we want to encode an integer m. Okay, so this is a positive integer, and we want to do this in the minimum number of bits. It has to be prefix free, because otherwise we can't recover it uniquely. But at the same time, so if we know that m lies between 0 and, or m lies between 1 and n, then you can store m using log n bits, but that is not efficient, because if if n is very large, or if m is very small, if there are no bounds on m, then in general it could be wasteful to do fixed length encoding of m. So in fact, you can store it using order, sorry. So any integer m can be encoded using ceil of log m plus 2 log m plus 1 bits. All right. So for example, the integer 100, you have a prefix-free encoding, which for the integer 100, it takes log 100 plus 2 log 100 plus 1 bits. For 1000, it requires log 1000 plus 2 log 1000 plus 1 bits. Okay, and the basic idea is the following. So first you look at the binary representation of m using log m bits. So the integer m can be represented using just log m bits. Okay, so this is some sequence, right? But then the problem with decoding this, with getting a prefix-free encoding of this, is that you don't even know what log m is, right? So you don't know where to stop. So what you can do is store log m using log m bits. Of log m using log m bits. Okay, so you store that, you prefix that to this, right, is something 0 1 0 0 0 0 0 0 maybe. So this is the binary representation using log m bits. But now you need to know what log n is, and in fact you can do that by storing it in unary. Of right, and what do I bring by unary representation? It is just a sequence of ones. So if you want to store a number k, then you just store k once followed by a 0. Okay, so this is a prefix-free representation. So how does decoding work? You first read the unary representation to get log m, and then read the next log m bits to get log m, and read the next log m bits in order to get m. Okay. All right. So we'll see an example of this in the next class. Since we're almost close to the ending time, we'll have a short quiz. Right, so the unary representation is the following. So if you want to represent a number, say 5, okay, you can represent it in unary by storing 5 ones followed by a 0. Right? So to decode, you just count the number of ones which occur before a 0. Right? So 0 would represent the integer 0, 1 0 would represent the integer 1, 1 1 0 would represent the integer 2, and so on. 1 1 1 0 would be 3, and so on. Okay. So here is the quiz. Let me know if you're not able to access the link.
Hello, sir.
Yes.
So in the first question, one option is there, the block minimum rate of compression bracket in the bracket blockwise encoding of x bar n for
Yes.
large n.
Yes.
So sir, this is the stationary Markov chain. So how do we do this blockwise encoding here?
So using the optimal compression algorithm.
Okay, sir. In this using optimal in the sense, this Hoffman, we can use any
Yeah,
like that.
anything, not necessarily Huffman or what you've seen so far. What would be the minimum rate of compression that one could achieve using any, yeah, using the best
Okay, sir.
possible compression algorithm?
Okay, sir. Got it.
Anurag, yeah, so you can include between A and B to include both A and B. So you can take 1 more minute to submit your answers. Has everyone submitted the solutions? Anyone yet to submit? Okay, so if there are no further submissions, then I'll stop accepting responses. Yeah. So what is the minimum rate of asymptotic rate of compression for a non-IID stationary and ergodic source?
Limit
It's,
time tends to infinity.
yeah, so it's the entropy rate. So for a general, so even for a stationary first order binary Markov chain, the minimum rate of compression is equal to the entropy rate, which in general could be less than the entropy. So if I do symbol-wise encoding, then the minimum rate of compression is always 1 bit, because I need exactly 1 bit to encode. But then if I do block-wise encoding, then I can achieve the entropy rate. And in general, the entropy rate could be much smaller than 1 bit. So the minimum rate of compression could be less than 1 bit. Okay, so so we'll end the class for today, but if you have any questions, I can answer them now.
So just a small confirmation. In the website, it was mentioned we need to write a LaTeX report or something for the paper presentation, but that's not needed, right?
It's not needed, yeah. So that's something that I'd like to clarify. So you don't have to submit a report, but you have to record a video and upload it. And in addition, there'll be a short Viva based on your presentation. Yeah.
And sir, in the video, like if the paper is a little bit longer, do you have to cover every aspect of it, or like the key aspect?
No, so I think I mentioned it in Piazza, but you should explain the problem statement and summarize what the results are, and give at least some overview of the techniques that they have involved. So I don't expect any proofs or anything, but if there is something particularly interesting about the paper, something very new, then I expect you to just spend a couple of minutes explaining that.
Okay, yeah, thank you.
So both the teammates can upload a single video, right?
Yes. So one video per group.
Okay.
So keep it between 10 to 15 minutes, a minimum of 10 minutes and a maximum of 15 minutes.
Sir, hello, sir.
Yes.
Can you discuss this first question? Because block only one option is correct, or I want to know the
Two
answer.
options are correct. The one option which is correct is, so if you do symbol-wise encoding, then you need exactly 1 bit. Right? The minimum rate of compression is 1 bit. If you do block-wise encoding, then the minimum rate of compression could be less than 1 bit. So those two options are correct.
Okay, sir.
So sir, a small doubt. So how can we interpret this limit n tends to infinity hxn by n?
So okay, so let's look at this expression. One sec. Okay, so let's first use the chain rule. So what is the quantity that we're interested in? H of xn divided by n. So if we use the chain rule, this is going to be summation I going from 1 through n, h of xi given x1 through xi minus 1 divided by n, right? So in fact, it turns out that any stationary and ergodic source, which is basically a source with memory, can be approximated by some kth order Markov source, that is where xi can depend on xi minus 1 all the way up to xi minus k. So if k equal to 1, then it's just a first order Markov source. For general k, we have a kth order Markov source. So this implies that each symbol can depend only on the past few symbols, not too much in the past. Okay, so for a general kth order Markov source, this term, the entropy rate, would turn out to be, so h of x1 plus h of x2 given x1 and so on up to h of xk given x1 through xk minus 1, and then all of the other terms depend only on the previous k terms, going from k plus 1 to n of h of xi given xi minus 1 through xi minus k whole divided by n. Okay? So if k is something which is finite and independent of n, and of course we know that this is a stationary sequence, this would just be h of x1 by n plus h of x2 given x1 by n, so on, h of xk given x1 through xk minus 1 divided by n plus n minus k, I guess minus k minus 1 times h of xk plus 1 given x1 through xk divided by n. Right, so this in fact converges to the kth order entropy, which is h of xk given x1 through xk. So for any stationary and ergodic sequence, the entropy rate in fact turns out to be some kth order entropy, or kth order conditional entropy, which is for some finite k. Okay, so this implies that the amount of memory that each symbol has is only k. So it can depend only it can only depend on the previous k symbols. Okay, and that is sort of one way to interpret this entropy rate. So in other words, it's the total amount of uncertainty in Xn, and that can be decomposed in the following fashion. So, and this in general could be much smaller than h of xk. Does that answer your question?
Yes, sir. Yes.
Sure. Okay, so Anu is asking the question, how can the expected length be less than the entropy? So we know that, so again, it's not the length, it is the compression rate, which is expected value of k of xn divided by n, right? And we know that the minimum rate of compression is equal to the entropy rate, right? And in Piazza, we also showed that for a first order Markov chain, limit as n tends to infinity h of xn by n is equal to h of x2 given x1. Right? So now consider a Markov chain with the following transition probabilities. So it's yes.
A small dot. So this h of xn is nothing but the joint entropy, right?
Correct. It's the joint entropy of n symbols.
Okay.
Okay, so consider a first order Markov chain where it stays in the current state with probability 1 minus p and transitions from 0 to 1 or 1 to 0 with probability p. The stationary distribution is half-half, right? But now for this, you can go later and then try to compute h of x2 given x1. So in fact, you can probably look at this and say, so what is h of x2 given x1 in this case?
One bit.
For general P?
No, sir, for this 1/2p.
No. So P is not 1/2, right? So stationary distribution is P x1. So P of x2 given x1 of...
In the question, it is given 1/2.
That is the initial distribution, right? That is the initial distribution. The transition probabilities could be something different. So maybe if I'm confusing you with the notation, then let us call this alpha. All right, so px2 given x1 is 1 minus alpha. Px2 given x1 of 1 given 1 is 1 minus alpha. Px2 given x1 of 0 given 1 is alpha, which is given x1 of 1 given 0. And px1 of 0 is x2 of 1. This is equal to half. Right? So for this, what is h of x2 given x1?
So the expression will be in terms of alpha.
Exactly, it will be in terms of alpha. But can you say what exactly it is equal to?
So summation of 1 minus alpha log to 1 by alpha plus alpha log to 1 by alpha.
Yeah, so that is, it's just the binary entropy of alpha, right?
Yes, sir.
Right, so this is the binary entropy of alpha. So if alpha is very small, right? So or if alpha is close to 1, this can be really small. So this can be close to 0. So in general, the average rate of compression that you can achieve could be arbitrarily small. So all of this is, of course, if you do blockwise encoding. All right, so any other questions? Okay, so if there are no further questions, then let's stop the meeting for today.